Welcome to Driven. I'm your host, Paul Perrone. We're going to learn and talk about AI, robotics, autonomous vehicles, and so much more. Check us out at driven.show on the web and give us a thumbs up or subscribe here if you like the show. So kick back or buckle up and become driven. Well, James, thank you so much for doing this. We go back a little bit. But you yourself, you've had a long career, influential role in computer science, particularly as the founder of the Java programming language, which I'm particularly enamored with, and millions of developers, downloads, devices. It's almost going to be 30 years, I guess now, since it was sort of.
Well, it depends on
Oh,
when you start the clock.
okay.
I think from the public announcement, 30 years is in like a year or two. It's like next year. But from the time that the first piece of Java code was written, it was in 92. So it's 32 years old on my clock.
Right. Wow, that's there's something I never knew. So maybe let's just dive right in, I guess, if you don't mind. How did Java sort of really come to be? I know you had been working with Sun Microsystems for a while, right out of Carnegie Mellon, I guess. Was that right?
Yep.
Yeah.
Well, I worked for IBM for a year and a half.
Okay. And then you went over to Sun, and was that in the earliest days of Sun? Was that who was the crew there? Was it
Bill, Andy, Scott, all the people that everybody knows, but really, it was the engineers that nobody remembers.
Okay. Were you like did you have like an employee number? Were you like number I when
So it's a slightly weird story because my employee number was 528.
Okay.
But a friend and I actually had lunch with Andy Bechtolsheim at Stanford, just after he had signed the papers with Scott and Vinod, and he was like, "You should come join us," and I was like, "Andy, you're," and part of it was that I had experience with Andy's engineering, and Andy's a really great engineer, but he tends to make stuff that is really aggressive. He pushes the parts. So he always starts out with reliability problems. And then it takes a while to get things to settle down. And at the time, IBM was also trying to get me to join, and I was looking at some of the stuff that IBM had, and it was way better than what Andy was starting with, because he was starting with the Motorola 68000. But what I didn't appreciate at the time was IBM's incredible ability to shoot itself in the foot. And Sun's ability, when it's, three guys and a dog, they can move pretty quickly. And so it took me like a year and a half to learn that lesson. And I eventually, joined Sun, having felt like I had spent the the last year and a half at um, a very unfunny clown car.
Right. So that was like kind of boot camp, and then you went over
Well,
and
it was my first job with a real industrial outfit,
yeah.
and you know, it was a real lesson in industrial politics.
Yeah, I can imagine. I actually had the opportunity to go down to Boca Raton to visit the building where they kind of made the PC, I guess is what I heard,
Yeah.
where it was kind of engineered and developed, and interesting old building. They've kind of revitalized it, but a lot of weird sort of nooks and crannies and stories, which I always find fascinating. The history of some of these um, uh, buildings and things where foundational technologies were created. But I guess that wasn't where you were at. I presumably were you down at that facility or kind of on the West Coast or
So it was kind of an odd deal. Um, my my manager was at IBM Research in Yorktown Heights, New York, which was sort of the belly of the beast. Um, the organization that I was a part of was headquartered in Stamford, Connecticut. The project that I was working on was this weird assemblage of people, some of whom were in Austin, Texas, um, and the Almaden lab in San Jose, and the Yorktown lab and the people at Stanford. And this was a few years ago. So instead of email, it was usually faster to just get it on an airplane. Uh, and because IBM had no detectable budgets, I was just getting on an airplane. At one point, I asked my boss, "So, what's my budget for travel?" And his answer was, "I have no idea. Just do whatever you need to do, and we'll figure out what your budget is when the finance guys complain." And they never did. So, yay.
never hit that threshold. Yeah.
Yeah.
Well, and then so then you at some point you jumped over to Sun, and what was your first kind of entrenchment and gig and activity there? Sun Microsystems. This must have been
Um, I Well, when I first got there, it was kind of like figure out what to work on, and I had sort of two choices. One was the Windows System group, and the other was the OS group. And as much as I loved everybody in the OS group, um, it felt like they really had their shit together. Um, and I was hoping to go, so I thought I could be more useful in the Windows System group. So that started me off on 5 years of writing graphics device drivers and learning how to render kanji. Uh,
kanji.
yeah, yeah. So one of the things I was involved in at the time was rendering fonts, and this is like the mid '80s.
Right.
So rendering fonts from spline outlines. Um, Today, it's a completely common thing to do. Back then, it was fairly unheard of. Um, and one of the parts of it was, okay, we have all these Asian customers and all these algorithms that work pretty well for um, sort of Roman fonts really fall apart on kanji.
Ah, okay.
Um, so I got to spend some quality time with um, folks in Japan and trying to understand that. And we eventually got better at it. So,
And was this the early was this Spark Station type platform at this point, or was it?
Um, no, the Spark Station was later.
Okay.
This was still in the era of the 68,000s and
Okay.
the 68020s, those sort of things. The Motorola chipsets.
Okay. Yeah, I think I first intersected with Sun workstations probably circa 1980, 89ish,
Yeah,
maybe not 90. Yeah. So I guess I can't remember if those were Spark based workstations
yeah.
by then or
By
not.
and they probably were.
Okay. Interesting. Interesting. So then so that's 89, 90, and then it sounds like it was just a 2 year sort of hop to the start of Java. What really what what spawned the, I know a little bit about the history of it from reading things, but what spawned the interest in that? Really, what was the the
Um,
idea or a collection of ideas that really drove home that, this.
there was a group of us that had become increasingly disgruntled by the fact that Sun seemed to be ignoring a completely gigantic market. Sun had become very data center obsessed, and it felt like there was a lot of stuff outside of data centers, and so we convinced Scott to let the group of originally four of us, eventually like 20 or 30 of us, um, go off in a corner and do some exploration. And we did a bunch of like world tours to go talk to people who made everything from VCRs to locomotives, um, and try to understand that world. Um, and I had I mean I had some backing in that world because my earliest jobs had all been as essentially a code monkey, for physicists and other scientists. Right, I was just a kid in college, who would do coding for research projects, and then I did end up learning random things. But when the system that you are uh, building software for is talking to a satellite or talking to a spectroheliograph or whatever, um, you kind of end up doing a lot of understanding how the how the boundary between the sort of virtual world of the computer and the sort of protons and neutrons of the rest of the universe.
Yeah, so now that sounds like when you mentioned VCRs too and locomotives, so that was more, so was it just sort of this world of embedded systems that you were sort of seeing of interest, or was it the emergence of the internet that you thought Sun was missing out on? Because.
So Sun was. I mean, one of the things that I really loved about Sun was that Sun lived and breathed the internet from day zero.
Okay.
Um, in 1984 when I joined Sun, it was already deep in the DNA. Um, I mean, I knew people like Bill Joy and talked to them, and when they founded the company, it was all about networking, and I was like deeply, deeply unhappy about IBM's really bizarre attitude towards networking. And when I was a grad student at Carnegie Mellon, everything was connected to a network. Now, admittedly, those were the hottest and fastest and coolest networks available at the time, which was Ethernet at 3 megabits, which is these days just barely a rounding error. Um, but Sun started from the very, very beginning as it's all about the network, and it was really hard to get a Sun workstation that didn't have a network port. And Sun just it just assumed that the whole universe of TCP/IP was going to win because the others were just stupid. I mean,
Yeah.
the IBM protocols, the DEC protocols, some of the Xerox protocols. The Xerox protocols that came out of PARC were pretty sensible. And in fact, they influenced pretty heavily TCP/IP. But the standards bodies and and they were just nuts. And we just had this almost religious belief that TCP and IP were going to win the war, and they did. They did, because they're incredibly straightforward, or at least they were really straightforward at the time. Um, you know, 35 years of hacking and adding bits and pieces to them has made them a lot more complicated,
Yeah.
and a lot more complicated than they should be. And then you look at HTTP, which was this protocol that was designed in an afternoon, and then evolved over decades, and has become kind of a nightmare. Implementing HTTP correctly with performance is a real ton of work.
So that's interesting. I never really thought about but I guess there was BitNet and DECnet, and there was these different. Those weren't TCP/IP based, or were they?
They weren't.
They weren't. So, and that was that was the original concept of ARPANET, right? To tie together these heterogeneous networks in some way.
Well,
Is that right?
so the ARPANET preceded the internet.
Hmm.
The ARPANET, it wasn't trying to tie networks together. It was just trying to get packets from A to B. And it was a really, really good learning experience. And the people who were involved in the middle of that, and I certainly wasn't in the middle of that. I was just kind of like on the edge of it. Um, um, and it came to be understood that what the issues were with the way that with the ARPANET protocol was put together. But one of the problems with most of the industrial protocols was that somebody would invent something and it would be frozen in time. It's really, really hard to evolve given the way that industrial politics work. And so rather than learning from things, you end up with these like stratified layers of newer and older stuff, and somehow or other you end up having to replace or implement all of the old versions because there might be somebody out there who speaks it. And of course that has infected the internet pretty badly today, which is why a lot of like TCP and HTTP is as miserable as it is. But that's just the way engineering works, right? You look at look at an archaeological dig site, right? And it's it's layers of stuff, and
Yeah.
that's what engineers build, is layers of stuff. Uh,
Right.
but the nice thing about the ARPANET was that there was a opportunity to learn from it and then replace it. So there were a lot of lessons learned, and then people did experiments. I was involved in some of the experiments, um, and you know all these like competing ideas, yada yada yada. Um, Having had something that functioned that people could compare it to was fabulous. Um, and then after a number of years, there was a flag day uh, where IP packets would flow in the wider network, and ARPANET packets would not.
Right.
I mean, there was this kind of, um, but there. I'm sure, I don't know how many ARPANET sites there were at the time. It was small. It was like 20 or 30,
I see.
maybe 100.
So the internet kind of came along, replaced all that, and there's a bit of a and I know there's a misconception that because of applets that Java was created in some ways, and maybe you tell me, was driven by sort of this internet initiative, but it sounds like the foundational idea behind it was to maybe address these embedded systems and or maybe like think about what do these embedded systems like VCRs and trains and what have you need that is not currently offered, and what can Sun at that time do about it, right? Is that the gist?
Well,
Or
yeah, close. Um,
okay.
because we had this opportunity to go and have these long conversations with engineers at companies that did the low level engineering on VCRs and locomotives and elevators and whatever. Um, we got to figure out what their problems were, and we would talk to some of the management folks and get views of what their problems were, and um, we were a bunch of engineers, right? So the way that we approach trying to understand a problem is we start building toys. Um, so we tried to, work our way through building some prototypes, and because it was kind of the path of least resistance, we were mostly um, building stuff around um, home entertainment, VCRs and stuff. Um, People somehow or other got the idea that we were, trying to be a consumer electronics group, and it was like, no, they're just the nice thing about doing software for home entertainment is that there's really nothing you can do that can cause somebody to die, right? If you're experimenting with control systems for like an elevator,
Yeah.
um, it's a really hard place to do software experiments, because bugs lead to a couple of tons of shattered steel at the bottom of a concrete shaft.
Right. So you were steering away from physical world interfaces, I guess, aside from maybe sensing, but maybe
Oh, well,
the
we were
actuation.
steering away from things that would cause blood to flow,
Right.
just
Okay.
just 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 because it made the engineering easier, right? It was
Yeah.
less hazardous. Um, but in later years, it was really entertaining talking to people who had picked up on some of that stuff and were doing things, actually doing stuff on locomotives and elevators and
Autonomous vehicles.
autonomous vehicles. Yeah.
Yeah. Yeah. Interesting. So I guess, but you had in mind, I guess, this concept of real time deterministic processing, that there might be a need for that. I think you were at some point, because you were involved with the Java real time
Yeah.
sort of variation that came along. Now that wasn't really for was that driven that wasn't driven by the consumer or entertainment devices, I presume,
Yeah.
or
Yeah.
was it?
Eh, so part of my brain knew this was a problem. If we were going to grow out of um, sort of the stuff we were doing, we really needed to handle low latency. Um, and, most of the key ideas were not mine. Um, we came upon this guy named Greg Balella. Um,
Oh yeah, I know Greg.
yeah. And, Greg had just done a PhD on control systems and um, the sort of boundary line between sort of hard real time and not really real time, and was really into scheduling theory and stuff like that. Um, so all the real ideas were his, um, but we built this thing, and it worked really well. Of course, the politics inside Sun did not work at all well, because by that time, Sun was making most of its money off of things that went into data centers. And when we talked to Sun management about some of this stuff, they'd say, "Well, what data center rack do we put it into? Where in the data center does it fit?" And it doesn't fit in the data center, except it
Right.
kind of does, right? Because there are customers who actually care about timeliness. So people who do things like stock trading, they really really care about milliseconds or microseconds. And at one point we were trying to turn Java real time into something that would work for the stock trading, and it actually did
Mhm.
work quite well. But there were complexities that um, you know that were just sort of hilarious. Um, but one of the things that's been interesting is that the original Java real time spec was was driven a lot by people who had a lot of really extensive real time experience, and then sort of
Mhm.
observing people who were using it. Um, they tended to avoid the parts that looked like traditional real time. They really, really liked having like a garbage collector. And because we had sort of a twisted version of the garbage collector with unusual rules, you could actually run real time code while the garbage collector was working. And we had done a bunch of work on trying to make the garbage collector have bounded maximum pause times. Um, and so all of the sort of special allocation zones and um, special real-time scheduling didn't get used as much as I would have thought. Uh,
Hmm.
but the work on low latency garbage collection carried on. And it actually started to get real mainstream acceptance. So
Oh,
like JDK 21 has a garbage collector that's got really, really, really good timing characteristics. Low overhead, low latency. Um, if you care to do a bit of tweaking, with one of the things about real-time garbage collectors is that you, to some extent, have to do a trade-off between latency and throughput. The more you try to build guaranteed latency, the more you end up taking a hit on throughput.
right.
And, you know, people have been working on this stuff since the dawn of time.
Yeah.
Um, so like one of the guys who was involved in Java real time in the early days, a guy named Kelvin. Um, he works at Amazon now, and he's doing low overhead, low latency garbage collectors. Um, and there are people at Red Hat doing that. There are people at Oracle doing that. There are people all over the world that are like focusing on that. And I think I'll not give numbers on what the latencies tend to be, but they're pretty good.
Yeah. Yeah. Well, I mean, you know, as you know, one of the facets of Java that we were, I was using it for was for robotics and then autonomous vehicles, where the vehicle has to be able to respond to events, and you can't have it sort of garbage collection kicking in at just the wrong
Right,
moment, right? So that's where real time Java was very, of certainly of interest, and also not generating garbage within this framework of
right,
code that we
right.
were working on. But then along the way, as multi core processors became more and more commercially prevalent and available, I guess the real time Java had, I guess, this concept of processor pinning. At least some of the JVM or incarnations of it where you could pin certain uh, threads or whatever to certain
Yeah,
cores, right? Um, and I'm not sure if sort of that ever carried over into sort of the standard non real time Java
yeah. No, it,
um,
it never really
platform.
did. But mostly because on average, people who play with things like that shoot themselves in the foot rather than make a positive difference. Um, you know, using sort of runtime analysis, it's usually better. But like one of the areas where this shows up in clouds is machines that have a non-uniform memory architecture, NUMA. Um, and that's pretty much all processors, um,
Hmm.
or at least all processors that are sufficiently beefy. The memory access times are not uniform. You access a piece of memory over here, and it costs this many nanoseconds, and you access a piece of memory over here, and it costs a different number of because you have to traverse different buses or um, and so people have done if you let people do manual placement of processes so that in trying to get threads close to their memory or device adapter or whatever, um, they're more likely to get it wrong than right.
Yeah,
Um,
yeah,
and so the sort of analysis that one does or basically hacks to try to make sure that the process that is spinning over some data structure is as close to that data structure in terms of the bus architecture as possible. Those tricks have come and gone over the years, because the sort of the cost trade-offs one another
Yeah.
have shifted, and
I mean, maybe it's more of a problem in, I don't know if it's just specific to robotics or just certain embedded applications, but I found it useful in the sense that this sort of major and minor frame concept where you have a frame or sort of a main thread that's just sort of doing sense plan act over and over again, and it's doing it within a certain, every 10 milliseconds or 100
yeah,
milliseconds, however and it's doing something on a periodic basis. And then sort of what's happening asynchronously is you're getting data in from a sensor like lidar or some sensor, and it's doing the perception. It's inferring, what is it that I'm seeing in this cloud of points? Is that a human? Is that a bird, a dog? And some of that can take, longer than you expect or
right,
whatever. And if that's happening kind of over here, but your main thread is going forward, and then your main thread detects, oh, we're not perceiving something fast enough. I'm going to slow the vehicle down, or I'm going to stop,
yeah,
right? In
yeah,
some case. And so that would be sort of that was sort of the interesting thing about being able to pin that sort of one, that thread to that core. And then on the flip side, there's also the concept of like a monitoring watchdog, right? That's
right,
just kind of the psychiatrist for the autonomy. It's, are you okay? Are you
yeah,
okay? Kind of
yeah,
thing. And that could be in a thread kind of doing
yeah.
its thing. And while some
It
of
is,
these more
it
asynchronous
is
things happen.
absolutely essential to be able to do like different levels of predictability, right?
Yeah.
And some things are just inherently unpredictable, right? So one of the things that I hear from people a lot is, they've architected their system around all these low level loops, and then they're trying to do long term planning in the same kind of discipline, right?
Yeah.
And so if you've got sensors saying, you know, I see a human over there, over there, right, right? You've got to have this total situation awareness um, construction. How do you represent and reason about um, the space around you? And that's never going to have a predictable timing, right? Because I mean, you can make it predictable by saying you're allocated 10 milliseconds to understand the universe around you. But then, the way that that's always built is, you've got 10 milliseconds and then you're cut off, right? And
Right.
that means, that the, as you're like iterating through cameras and integrating them in, that, you get cut off before you integrate the data from the camera that sees the small child chasing after a bouncing ball, right?
Right.
And so you've got to be a little more flexible, and you've got to handle much more complex data structures. I mean, when you're doing, the low level heartbeat level things, um, it's really hard to do those and have complex data structures.
Hmm.
Um, Whereas once you're, up at the level of doing situation awareness, you unavoidably end up with complex models. And you can try to make the complex models simpler, but then you almost always end up losing something. Um, and I've become a real fan of pushing hard on, whatever kind of situation awareness map you've got, and putting a lot of intelligence to that, and having discoveries from it kind of filter out below. So it's like, oh, small child over there, let's not go there.
Right. Yeah. Yeah. Now with what's your take on? I mean, AI has waxed and waned throughout my own career, and I'm sure your career. It's had winners, um, as they refer to them. But now there's been like sort of a new waxing on this generative AI
Yeah.
technology, GPT, LLMs, and what have you. And obviously, neural networks are, they're inherently probabilistic machines. They're not
Right.
predictable. There's no way to determine what it's going to do, and there's no way, if once it determines something, to really figure out why it made that decision, because you're looking at a bunch of numbers, weights,
Right. Right.
right,
Right.
and a network, and so that makes it difficult or it can make it difficult for production grade application to an autonomous vehicle. Yet you see a lot of companies or robotics, right, using it because it's really great at pattern detection and perceiving, and maybe even saying, hey, there's that kid with the ball, right, or no, that's really a pelican, whatever whatever it may whatever it may decide. And but then there's like adversarial machine learning and all these things that can kind of really sort of make the system hallucinate. I guess any thoughts on the applicability of that technology to these sort of real-time deterministic, or these embedded types of
Um,
applications where you kind of got an
so the first thing I like to do in conversations like this is get rid of the term AI.
yeah,
It becomes this marketing wrapper that blurs the boundaries between things. Um, and I tend to, certainly in my head, think of all of these things as advanced statistical techniques. And, you know, these things are statistical. And sort of inherent in statistics is that you don't always get it right. Um, and some things, are more prone to hallucinations than others. Um, but in the real world, there are lots of things that are inherently kind of statistical. So human vision, if you're looking at a tree and you think there's a bird up there, and then you go, no, it was just a puff of wind moving some leaves in a weird way. Um, you know, even human vision is inherently pretty statistical. Um, but and humans are going to miss it, are going to miss things. I mean, if you've got a dense hedge and a kid is playing on the other side of it, you can't see it. If there's a gap in the hedge and the kid dashes out from it chasing a ball, um, you missed it. You missed seeing the kid when he was behind the opaque hedge. Um, and that's a real problem, because that's what causes kids to die. And some there are other things like I mean there are people who are using Gen AI to write software, and that's pretty cool. Um, these days, it feels to me like it's still in the kind of party trick phase, because all the generators, they generate stuff that might work, right? So if you're a software engineer and you're trying to use this stuff, you have to really know that whatever comes out of the Gen AI chat box is just a suggestion. It's not definitely going to work, but with a lot of complex systems, I guess I've gone to where these Gen AI systems for writing software are, I think, most usefully viewed as the documentation that the people who build the systems didn't write, right? So if you say, how do I connect A to B, and software service A and software service B are things you don't know much about, because you know that this time series thing and this graphing thing are things that you want to connect, but you've never used them before. And you say, how do I connect, the time series database to the graph drawing system? It will give you a suggestion, and that can help. So they can be, like a helpful person along the road who kind of points the way. In the days before GPS navigation, when you pull up to the side of the road and ask somebody, how do I get to, and they'd say, well, I think you go here and there and that, and that's kind of the way I think of sort of the Chat GPT like things. Now they're
Yeah.
getting better at a hellacious rate, and
Yeah.
I'm perfectly fine with them so long as people keep in mind that they make errors. There's no guarantee that they're right. They're not like some of the automatic reasoning systems, the ones that people use for proving software correct. Those tend to be pretty rock solid. Theorem provers tend to be, they all give you like one of three answers: yes, no, and eh. And the fact that they can tell the difference between yes and no and is pretty amazing. And when you find errors in a proof, it's usually not the theorem proving engine that caused the error. It's the inputs to it, right? The inputs, in terms of the specifications or the sort of preconditions and postconditions that are fed in. But the reasoning tends to be completely solid. But when you use things that are inherently deeply statistical, they're fine so long as you account for the fact that they are statistical, that you have some way of checking that they are right or wrong. There's an interesting field of algorithms. There are algorithms that are sort of search algorithms that tend to take exponential time. NP complete problems, right? And they're ones where verifying the result can be done in polynomial time, but actually computing the answer can't be done in polynomial time. But it turns out that in a lot of areas of NP complete algorithms, there are heuristic hacks that can help you a lot, so that you can actually find answers to these problems in much faster than exponential time. So
Yeah.
in a past life, I really cared about the graph isomorphism problem. Turns out a lot of the time you can answer the graph isomorphism question in linear time. But in the general case, it's exponential time. And a lot of these statistical techniques that show up in generative AI, they're actually pretty good at making guesses as to what might be a good solution to one of these NP complete problems. And then you use it to guess, and then you verify. And if the verify is false, then you just have it guess again.
Yeah. You
Yeah,
iterate.
you
Yeah.
you iterate on the guesses, right? And if you've got a way of
Mm.
validating whether or not the guess was right, um, you can do that. Um, but if
Yeah.
you need to have like the most efficient, like say you're trying to find the most efficient path between A and B, um, guessing paths between A and B, and then saying, does this work?
Yeah.
Is unlikely to get you a really efficient path, right? You need for something like that, you need something deterministic, and it's probably going to look a lot like Dijkstra's algorithm. Um,
Well, one of the things that I would share is that I've personally, well, and we found ChatGPT and other generative AI methods um, useful at generating um, code. In fact, we've generated Java code, right? That can be fairly simple. That maybe like having it implement a method or even a graphical interface that does something very small and self-contained and well defined. You do have to make sure it does it correctly and you iterate, but you can get to a result maybe right now 10 times faster than if you told somebody to go do that and they went and did it for these small, fairly self-contained problems, just personal
yeah,
experience, right? But then the question is how do you create this larger um implement this larger algorithm like you might be able to tell it here's one step in the process of an automated vehicle that I wanted to do, and here's another step, but it's not going to be really good at sort of creating the orchestration of all that. But you can say, hey, give me an algorithm for lane keeping or something, and it's a broader problem to solve, and it might sort of sketch out the methods and not implement them and tell you here's like an algorithm and a structure, and it gives you sort of some ideas for at least maybe how to start with certain
yeah,
things. But then you can kind of drill down and say, now create this substructure, like this specific sort of method, and then you can sort of verify at that level.
right.
And I found sort of that taking this into the space of autonomy, for example, like creating, like, because already decomposed a lot of things into like an autonomous maneuver into modules and sort of atomic elements, steps that need to be taken in the course of a maneuver, and then actions that are taking within those steps, and the conditions that trigger the advancement along the path of this sort of state machine, if you will, of implementing this maneuver. And so it can be used to kind of generate some of these elemental aspects, the code that implements these elemental aspects. And then once you train it, like what as to what those elemental aspects are, it can actually start to stitch together the maneuvers themselves. And not perfect, still early, but there's definitely something there
Yeah,
that
yeah. There's
is
there's there's definitely something there. In general, I'm a fan. Um, I just keep wanting people to pay attention to the fact that these things aren't perfect, right? So you read these hysterical stories of people using Chat GPT to do things like generate legal briefs,
right.
and they sort of a cursory glance over it, it looks fine, but it references, case law that does not exist. Because it just knows that a legal brief kind of looks like this and the words kind of flow like that. It doesn't understand any of the reasoning behind it. But, so long as you are probing into areas where the training data has a lot of examples that kind of look like what you want, then you're fine.
Yeah.
But you still do.
That
Yeah.
Yeah, that's funny because that's an example. You're giving an example of people who are just ready to just give up thinking to the machines. They're like, you just do it. I trust it. But in fact, you're hitting on a key point. Of course, is it's more of a you have to co-pilot these things. You can get it to augment your capability
Yeah.
as a human being and make you more productive, but you still have to think and you have to interact and verify and check the work and make it sort of get you to the right place.
Yeah. And so you, particularly from people who are, in marketing and PR, they're the messages that they come up with are sort of like, yeah, chill, go to the beach, let the AI take care of all of that stuff. And oh, guess what? Bonus, you don't have to pay software engineers. And it's like, no, actually, this is just a tool for software engineers. You're not going to need less software engineers.
Right.
Um, and the one downside for me from this is that, you know, wearing my, as a software engineer, the thing I enjoy the most is writing code, and the thing I hate the most is testing code. And the way that most of these coding AI systems work, they decrease the amount of time I spend on the enjoyable part of the job, and they make the painful part of the job more painful.
Right. Right.
And
Until
certainly they never, these Gen AI systems are. It's hard to get them to pay attention to issues like, I need something that sorts this, and I need a test suite for it.
I've heard this analogy and I want to see if you think this flies or if it's just completely bogus. And that is, back in the day, we used to do low level programming and then operating systems came along and then we were at this next level. And of course, the layered software architecture, Java provided also an abstraction of things that people used to do at a very low level. And is this just another layer that we can leverage as a tool as software developers to make us more productive and have it do um, very mechanical and repetitive things and
Yeah,
maybe
yeah.
even at scale. Yeah,
As an engine that will deal with the boilerplate, great. Um, Although a lot of modern systems have a lot more boilerplate than than they really ought to. I mean, there's a definite failure of system design in the extent to which software engineers will go to their favorite coding website, search for some terms, and then cut and paste. And that's kind of what people end up doing with Gen AI. But you mentioned the sort of layers of things, right? When I started programming, everything was done in assembler. At least anybody who called themselves a real software engineer you knew how to do assembler because that's what you had to do. Um, and I'm sure that if you gave me a PDP-8 and asked me to write an assembly code routine, I could still do it quite easily. Because those are the sort of traumatic experiences that sort of like burn themselves into your brain, right? And there would be like scientists who would say, "Yeah, that's too hard," and they'd use languages like Fortran, and then they would hire people like me to make their Fortran work, or to write this right little inner loop in assembly code. But eventually, people started to trust code generators. But the thing about those layers of tooling is that there's some really rigorous reasoning that goes on in the constructions that they do, right? The figuring out of how to lay out the assembly code instructions by a modern compiler is deeply complex. It's if you're like a human these days trying to write optimal assembly code is really, really difficult because there are all kinds of nuances in timing and pipelining and all the rest of that if you want to get the absolute best performance, is really hard. And so people are like, yeah, just let the machine do it, because modern code generators are great. Modern storage management, automatic storage management, is great. Things like garbage collectors are impossible monsters to debug. But once they're debugged and they're solid and you believe in them, they are such a lifesaver. And so like, I think that some of the Gen AI tools that are starting to emerge are going to go on that path. And it's pretty interesting. But people shouldn't be confused into thinking that we're there already.
Right. Well, absolutely. I couldn't agree more. And the I guess, yeah, it's a bit of a question as to whether it's, it's going, are we on the path to AGI with this technology, this sort of LLM and or Gen AI technology, um, or is it just going to hit sort of a stopping point? Because I think back to like 4GL, fourth generation languages, and graphical tools like UML tools that were just going to generate all this code for you. Were going to be like the thing, right? That made programming easy, but none of that ever came to fruition, at least for in my world.
Yeah.
And I don't know of a lot of people who are doing that. I don't know anybody. And so it was sort of this promise, and then it didn't come through. And I kind of wonder if, and it's all crystal ball kind of projection, but
Yeah. And I think
is
it's
is
the same kind of what if kind of
yeah.
question, right? Have to see how some of this stuff evolves. And like the 4GL stuff, I always thought was kind of comical, because the people doing 4GL work, they could make stuff work really, 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 really well for really narrow domains. And the challenge was always, okay, so this 4GL is really great for this narrow 3% of the problem. Where does it help me with the other 97%?
Right.
Right. And with most 4GLs, you could see how they could be augmented to broaden the set of problems that they could be used to solve. But that would be a Herculean amount of work.
Yeah.
Um, and are there ways that you could, make that better,
Yeah.
make that broader? And the scope of problems that you can handle with, you know, just sort of today's programming languages, um, is incredibly broad. And humans are incredibly flexible. Um, and so to what extent is it going to be possible for the Gen AI folks to, in some sense, um, fulfill the promise of 4GLs?
Yeah. And those things also used to, as you I'm sure know, would generate code, or some of these tools would generate code that was nearly unintelligible for a human, a developer to figure out how to like tweak or modify, but you had to do that to get it to work.
Yeah,
And then and then it was very difficult to kind of reverse engineer it back into the
yeah,
tool, and kind of seen a similar thing with Gen AI, in that I went through a process where I asked it to do something, and it generated, actually I was asking it to take these XML files that are in this certain structure and reverse engineer and create me a diagram that showed the relationships in this certain way based on how these files were defined. And it kind of did it right, and then I was iterating with it, and then I told it to do something, and then it did something wrong, and then I asked it to kind of roll back to where it was, and it couldn't do it.
yeah,
It couldn't and so you were at a stopping point now. It's like now I had to, you just gotta start the dialogue all over again, because it
yeah,
couldn't roll back well, you know?
yeah, yeah. All of these things tend to be, um, very waterfall.
Yeah.
You could do this, then this, then this, and one of the big things with modern uh, software development methodology is you've got to be able to do a loop, right? It's write, test, and it's like, oh no, there's a test. Got to fix that. Got to fix that. How do you do that? How do you do that engineering loop? And many of these tools are too primitive for that right now.
Yeah. Yeah, they have to be able to ingest what you have modified to kind of, but, to some extent, I think some of these Gen AI tools are starting to do that. They'll take the mods that you make and understand it, and hopefully incorporate it into the output. But
Yeah, they're
um,
they're they're certainly getting better,
yeah,
and in some domains they're wonderful. If you're trying to create meme images, um, they're and you use some of these image generators, they're just so entertaining.
yes, yes. I like it to ask it sometimes to generate press releases for the company in the style of like Hunter Thompson, and those are just hilarious to read.
Yeah, 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 yeah.
Um, how can Java, to your knowledge, integrate with, or how is it integrating well with this sort of Gen AI tech, right now? And just another kind of question related to that is, NVIDIA has really kind of grown as a company with their, you know, processors that were once designed for graphical processing, and now they've applied it to these neural networks, different from sort of the other architectures in the world. Um, do you think that's sort of the processing architecture that's needed, and if so, how can Java leverage those kinds of processing architectures, whereas they traditionally haven't been ported to them?
Um, I mean, they always end up being APIs. Um, there's some pretty decent APIs out there. Um, Many of the Gen AI services are are ones that you have to talk to over the net, right? So it's an HTTP request with some authorization
Right.
and a bag of text. Um, and that works perfectly well for some things. The round trip delays mean that they get a little clunky. But that's kind of a universe where the APIs are the simplest. Um, and I don't think that there's anything particularly special or not special about Java for uh, doing those APIs.
Yeah. I guess I'm thinking about the embedded side of things as usual, like where you want to do it on a mobile platform, right?
Yeah,
Something that can move around. And you might not want to go to the cloud for that. You might have something on premise or
yeah.
in
So if we're doing like the recognition part of things, um, but those end up being very low level hardware-ish things, right? In order to and on mobile, it might be an NVIDIA chip. Good chance that it's like a Qualcomm chip or an Apple chip. Um, one of the ARM flavors that's got some kind of matrix multiply.
yeah.
Um,
I guess, yeah, mobile phones, but like embedded computers that might be on board or part of a robot control system or onboard a vehicle or something,
right,
could be anything.
and Nvidia's got a booming business in these high compute throughput designed for automobiles, things that are you get these like dev boards that are relatively small, but they run hot as hell and have ports that you can plug in a dozen cameras to, um, and since the architecture of those things is designed from the hardware out, um, they're all pretty idiosyncratic. They're all pretty different, and where things like Java and interfaces really shine is when people have like a roughly common notion to how like a network channel works. For example, there's TCP, the internet protocols,
Mhm.
um, and just exactly how the device works is irrelevant because there's this sort of abstraction layer, and all the network things at the end, they all work quite differently, and yet they do sort of the same basic things, and that lets you build APIs that abstract up from them. Um, right now, most of the hardware is so idiosyncratic that it's hard to come up with abstractions that span across a lot of different chipsets.
Yeah.
Um, I mean, just the wars around CUDA and the sort of industrial GPU interfaces. Um, it's going to be hard for any programming language um, to be particularly helpful until some of these low level conceptual sort of cross platform concepts kind of shake out. I mean, in some domains, things like floating point arithmetic. Floating point arithmetic for years was just a mess because every hardware manufacturer had their own notion of how to do floating point. Um, and then IEEE 754 came along and just made sense of things. And manufacturers started realizing that there was absolutely nothing to be gained by being different than IEEE 754. But right now, all the manufacturers are duking it out, and they're all incompatible, and mostly as they go from generation to generation on their own stuff, they're pretty good, but they're not where they really, really, really need to be yet.
Huh. You think I remember back in the day reading when I was like studying like VLSI, I guess it was, and then ULSI, a book by like Carver Mead from
Yeah,
Caltech, because he did a lot with neural nets, and thought it was really interesting that he's coming up with hardware architectures that were specifically designed to implement and model neurons very
right,
very efficiently. And while the NVIDIA processors kind of came from the graphic processing world, and they just found sort of an application. Any thoughts on novel compute architectures out there that might come along and sort of really be like the thing that launch and propel neural network based applications to the next level?
oh man. um Once upon a time there used to be this field of machines that were called systolic array machines, that were a lot like a modern GPU, um, and they were just like a mesh of processors. They were the um, single instruction, multiple data stream architectures,
Mhm.
um, and it's always felt like there was there ought to be some way out of this maze of chaos. Um, One of the projects that I did in grad school was a compiler for this um, very chaotic, crazy number of buses CPU that was part of the memory switching architecture, and it was really the bus controller for a significant multiprocessor, and people always wrote code for it in assembler, and I wrote a high level language for it that wasn't exactly like C or whatever, and I probably could have made C work on it. Um, it had the interesting observation at the end of that exercise was that the way to make that massive multiprocessor faster was to just take all the processors, throw them in the garbage, and run all your code on the bus controller.
Hmm.
The bus controller was actually faster than all the processors combined, um, and that I thought was kind of hysterical at the time. Um, but that was a compiler that was designed specifically around one very particular CPU architecture, um, and it feels like there's interesting stuff to sort out here, um, but the politics are just all wrong for any progress to really be made. Um, you've got the king of the mountain, who's got their own APIs. They have no particular incentive to let anybody else climb the mountain. They're they're the places where the second tier people find success is in, like, embedded recognition, right? The kind of stuff that happens on your iPhone or Android phone, or um, you know
Yeah.
and what are they? It just feels like the force vectors in the politics are not aligned, um, to allow clarity to emerge.
Yeah. Yeah. No, I hear that. I guess I always thought of Java as the great democratizer of of programming platforms and platform software platforms to enable you to kind of, well, write once, run anywhere, right? And maybe as we move forward into this this new era, this next era of compute activities that are happening, that it could still be leveraged to do that in some way.
Right. Well, but
Um,
Java, it sort of rides on top of other standards that have emerged, right? So it's like IEEE 754. It's the fact that byte addressable memory architectures have won. Um, how many people remember computers whose word size was like 60 bits, um, or 12 bits, or 18 bits? I mean, now that the byte sizes are 8, people just assume that that's the way things are. But that was a standardization battle that had to be fought.
yeah,
Um, and things like a lot of the libraries depend on the fact that people have kind of coalesced around the POSIX standard, um, and in particular about the around the Linux expansion of the POSIX standard. They, having standards like that you can build around, makes things like Java possible, right?
yeah,
Back in the day when you had machines like, so for instance, I'm sure very few people listening to this remember Multics. Um, but Multics didn't really have file I/O. The way you wrote to a disk file was you said, "Give me a pointer to a bag of bytes," and then you just did memory stores. It was kind of like an OS built around mmap.
hmm,
Um, and you could make that look like, like a streaming I/O device that you just go right to. But in its heart of hearts, that's not what it did. Except under the sheets, you know, that's kind of what it did. And having a lot of these models sort out is what gives you the ability to, start building some unifying abstractions along them. Um, and it feels like the generative AI world is really, really close, and probably it's kind of there, but the industrial politics are just brutal.
well, what are your thoughts on sort of the direction of, sort of the ongoing direction of Java, sort of under Oracle, if you care to comment, including your perspective on sort of that sort of how they took on Java and what have you from there. Is that something that you can comment on, or
Um, so I've actually been surprisingly happy.
okay?
Um, I mean, they've been moving fairly slowly and deliberately, um, but they also have the problem that they have many, 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 many millions of pieces of software and software developers out there that they there's a limit to how much you can change before you piss people off
Yeah.
or break things. Um, but a bunch of the crew that's there are people who used to work for Sun. Um, every now and then I get to, I have chats with Brian Getz and some of the others, and um, I'm really loving what they've been doing. And every now and then you know, I mean, I had dinner with Brian not long ago, and I was all like, "Well, why didn't you do this?" And it's like, well, because you follow that through and you find that, and then you know, such and such a percentage of all apps break. And even at small percentages, like if you broke 1% of all apps, that's still millions.
Yeah.
You
That's
know,
it's a tough problem. Yeah.
there are no, so they have to be um, really, really careful about backward compatibility. And with the module system that came in um, with JDK9, which is something that we had talked about for years. That um, and the module system was kind of like the one time that significant breakage was ever done in the evolution of the platform. And that's pain that's still going on, and we're up to JDK 21 now. um, I do all of my work on JDK 21. It flies like the wind. um, and they've been doing a lot to update the language side of things, and the sort of low level APIs and such. The the new Loom threading models with really lightweight threads, and the way that interacts with I/O and such. Um, that's pretty nice.
Yeah.
Um, and I've been completely addicted to patterns. The you know instance of and such things, that where you can and the sort of pattern switch statements is like, yes, that's the nail in the coffin of things I yearned for from Simula. Um,
Do you I guess Oracle, especially because of their large enterprise footprint, and Java, of course, was most popular in the enterprise. Um, and and I, of course, used it in that capacity at one point, but very much in the embedded space still. And do you think with the sort of Gen AI growth that if that, I mean, that's still, of course, can be an enterprise thing, but do you see Oracle or sort of the Java community um, kind of putting more energy in the future at all into sort of the embedded real time applications of it, or is that just sort of forever kind of gonna stay at sort of a slow simmer?
I suspect it's going to be a slow simmer. Um, I mean, as a general principle, energy follows need.
Yeah.
Um, and the number of sort of enterprise level software tasks to be done is like completely gigantic. Um, in the embedded world, it tends to be a smaller number of people, um, and just a crazy volume of devices. Um, yeah, you know, I I just finished replacing all the light switches in my house for the fourth time. You know, it's like yet another evolution of the smart home technology standards. Um, and, you know, the number of people who are involved in the Matter standard is pretty small compared to the number of people involved in, say, banking.
Yeah. Yeah.
Uh, and you know they you know their primary constraint ends up being, you know, millipennies in bill of materials. Um, you know, most of the embedded stuff that I've done has been, you know, on processors that are, you know, about a Raspberry Pi in power. Um, I mean, back in the day, um, you know, the processors that I was using were in, you know, like the machine I learned to write software on had 4K of RAM, and if you were very careful, you could get it up to about a megahertz.
Wow.
Um, so you know, the tiniest embedded system you could imagine today. Um, and actually, most smart cards have more oomph than that. Um,
You might be interested to know, I guess, well, Intel Capital had sort of, they had invested in us and we were working with Wind River. And so we were using a real-time JVM. We did a demo on on a vehicle that at a show where we had, you know, some lidar and just it was just autonomously driving around, avoiding obstacles and what have you. And this is a while ago, but we took our the same software platform and ran it on a Raspberry Pi. And it was getting data from two lidar. It was, you know, getting data from GPS, of course, and doing everything that we were doing on this larger processor platform on a Raspberry Pi. So super efficient, Java autonomous vehicle processing platform running on a Pi. It was magnificent.
oh, I mean, Raspberry Pis are so much more powerful than the biggest supercomputers of, you know, not too many decades ago.
Right.
Uh, I mean, you know, the Cray One supercomputer that shows up in a lot of old movies is, you know, has about the same amount of compute as like my watch.
Right.
You know, so you know, Raspberry Pis are remarkably beefy.
Yeah.
You know, running Java on a Raspberry Pi is completely straightforward.
Just the
Uh,
economics of it, of course, is, you know, amazing too. I mean, this was like a $30 Pi platform that we had. So it was,
yeah, yeah, and you know, when what you're putting that on is, you know, a $10,000 to $20,000 vehicle, um, then it's done in the noise. If you're
right.
trying to put it on on, you know, like a child safety monitor that you put in your kid's bedroom, um, then it doesn't work.
Yeah.
Um, the math just fails. But it's getting closer and closer and closer.
Oh, yeah. Well,
And
you've done some work with robotics too. When you left Sun, you were at Liquid Robotics, right? So can you share any sort of um, like interesting facets of what you were doing there, and you know, and sort of maybe it was not real time embedded, but sort of not just using Java, but other programming approaches for your work there.
yeah, so you know, you know, it was these autonomous marine vehicles. Um, the processor was roughly a Raspberry Pi. Actually, a you know a modern Raspberry Pi is much more powerful than the processors that we had that we were using in those. Um, but there was a layering of sort of temporal constraints. At the very bottom, the stuff that had the tightest constraints. Because this is a device that has pieces here, pieces there. It's all connected by network buses. It was actually mostly CAN bus for reasons that just make my head explode. And I will always hate, loathe, detest, deride CAN bus for being like completely awful. But largely because
Is it the bit alignments that like being an obsessive compulsive person, the alignments of the misalignments of the bits into different fields just drives me batty.
yeah, it's like all of that. And one of the problems with CAN bus is that there are many different flavors, and so the decision around CAN bus was made before I arrived, and it was made by a bunch of electrical engineers who really didn't know what they were doing. And so one of the things about the flavor of CAN bus that we used was that it had a central master. So it meant that the central processor could make requests to other things, but they couldn't send messages up to the central processor. So you'd have something like a magnetometer, a compass, and rather than just say have a magnetometer send a message up the stream when things had changed, you had to poll it. You'd have to say, what is your reading now? What is your reading now? And we would have to go through and poll every freaking device, even though most of them almost never had changing values. It's like, hello, Mr. Battery Controller. Are you on fire? No. Good. Thank you. Thank you for consuming that bit of bus bandwidth.
Right.
And so we tended to put the processors that had tight timing constraints close to the actuators that they were, so that like there was a unit with a rudder, and there was a processor that talked to it, and it was I forget what kind of processor it was, but we ended up doing that using running FreeRTOS on it and just writing C code. It was really simple software, and it had a really tight, very predictable timing loop, and we had a protocol on the CAN bus that we would use to tell it what to do.
Were you using Java to making uh C API calls for the CAN bus interface, or did you do something?
Um, so um, particularly at the time, finding CAN bus software that worked reliably and was affordable. CAN is the standard, but finding like an open source implementation of a CAN IO stack was not possible. so we found one that was a commercial one, but it was kind of at a price point we could afford because we were a little startup company, and that meant it was more than slightly flaky.
Yeah.
Um, and so the integration strategy that worked was that we ended up using was that the company that gave us the CAN bus stack had had a command line tool that was for debugging um, the CAN bus protocol. So when it saw a message, it would put something out on the it was all serial line. Or you could send it a piece of text and it would send that as that would turn into a CAN bus message. So we ended up literally just having a pipe from the Java process to the debugging tool,
Right.
um, because all the other paths that we tried, we couldn't get them to be solid enough.
Yeah.
I mean, it was just vile. I just couldn't believe that that's kind of where we landed. Um, that this software API was such a POS
Yeah.
that
Well,
it's like,
one thing I'll share is we've like earlier we used a lot of like CAN to Ethernet converters. You just buy them that they can be as cheap as under $100. They can be a couple $100, and so you get
yeah,
you get the CAN into Ethernet, and then we rewrote a bunch of software that just sort of created objects around like the standard format, the long format of the different CAN messages, the J whatever standard number it was. So and so that helped a little bit, but I did some of that programming, and I remember being just irritated beyond belief about all the like trying to figure out things at this bit level, like this
uh,
field.
it's horrible. It's despicable.
Yeah, it
But
makes me
like,
nauseous
like
to
in our
talk
in
about.
our case, the problem with the CAN to Ethernet adapters um, is that they all consume power,
Yeah, yeah, yeah,
and the devices we were building cost at least $100,000. Um, so money was not particularly an object around components. It was all about the power budget,
sure, sure, yeah,
and the power budget is what drove the selection of the version of CAN that was used. Um, and once that was changed and various boards were designed, there was no changing it. It was just like no.
yeah,
So we were just stuck with it. So it ended up being a horrible bunch of bubble gum. Um, but it did work, right?
yeah,
And and the Java code is where all of the high level analysis was done. Everything from deciding, you know, what the rudder angle should be to situation awareness, trying to figure out, what things we could collide with or were around us. What the collision outlook was, figuring out how to respond to um, possible colliders.
uh,
It was really all, and at the same time, managing the network link because we were streaming data through a satellite link, and that was all managed centrally in the Java code. All the queue management and shit for like, because like in that world, when you're dealing heavily with like satellite links or um, cell phone links that are really really stretched, um, they're flaky.
uh, interesting, interesting. Well, from there, I guess you went. you're a distinguished engineer at Amazon Web Services. Is it Amazon Web Services in particular? Is that the
Yep.
yeah?
Yep.
And you've got this thing called Greenglass that you've been working on.
Green, yep.
Green grass, right?
Yes.
Okay. I said green glass. Okay. Green grass. What's that? What's green grass in a nutshell?
So it's a software management framework um, that you run on an IoT device. It's really designed for sort of Raspberry Pi grade devices and above. Um, and it manages, installing your software, um, doing all the sort of housekeeping tasks. There's a um, a whole ecosystem of plugins that handle things like different forms of communication with the cloud, how you deal with flaky networking, how you deal with authentication, um, and also how you management of the device, especially when you have large numbers of devices. So if you've got um, a large number of like utility meters, um, how do you upgrade the software on a couple million utility meters? Greengrass manages all of that.
Hmm.
It manages all of the maintenance of information for like, how is the upgrade going? What kind of failures are we seeing in the upgrade process? You can do things like say, you can divide your fleet of devices into subfleets, right? So you could have, a really small fleet that is the one device on my desk. And then you can have a bigger fleet that's, the QA lab. And then you can have like the bigger fleet that is, all the gas meters in pick your country.
Hmm.
And you can say, okay, so roll out this software upgrade, you know, but like upgrade them slowly. Do kind of a rolling upgrade.
Mhm.
And the real reason for doing a rolling upgrade is that when you test things, you miss something, right? And so you can say, okay, so do this as a rolling upgrade. Start with like 1% an hour or 1% a day, and if there are errors, and then you get to monitor the errors that are happening, and some of the errors are just that device got driven over by a car, so it's never going to respond to you've got a bug in the upgrade software,
Yeah.
um, in the upgraded software, and so you get to manage that, and then as you get more comfortable with your upgrade, you can turn up the dial, and you can upgrade 1 million devices in maybe not minutes, but certainly hours.
Wow.
Um,
Wow.
and managing data streams of both task telemetry and sort of maintenance information, and yeah, it's when you build an IoT device, there's the thing that you need to do with it's a temperature sensor, in this and this, and then you start thinking, oh, I want to build a whole lot of them. I want to know how to do everything from software upgrades to security intrusion detection. A lot of that is pretty hard.
Yeah.
But it's also similar across a lot of family of devices. Um, and so like one of the things that we put a lot of effort into is how do you build a secure device? Um, how do you build a device that's unhackable? And we make sure that all the security solutions are really really tight. But and in the average IoT device shop, the last thing they think about is security because the device works fine. I mean, who cares? Adding all of this security stuff, it's just a pain in the ass. It's not a feature that we can write up in our marketing literature. So
Right.
yeah, okay, so okay, I'll do this right thing. I'll use SSH and I'll just have one password for all of them, and because I'm a lazy sod, it'll just be root. Um, and that's kind of standard practice, right? And so Greengrass does things like, no, you have to use all the right public key things. You have to have certificates, security certificates. You have to rotate the security certificates. Um, and when it's a device talking to the cloud, you have to be able to punch a hole through whatever firewalls you've got, and NAT security and yada yada whatever. And we manage all that. So it's one of the catchphrases at Amazon is we do the undifferentiated um, heavy lifting. Um, so Greengrass basically does the hard but boring boilerplate of building a device that needs to talk to the cloud.
Interesting, interesting. And so now, and this is the software that goes onto these different devices, I guess, right? Or is it?
Yeah.
So it's So is this also a Java based
Yep.
framework?
Yep.
Okay, yeah, fantastic.
Yeah.
Yeah,
Yeah. Yeah.
interesting.
And so it works pretty well on things that are sort of Pi, Raspberry Pi and above.
And have you stripped away, like, because there used to be Java ME and all these things, but is it like leveraging the modules, a stripped away version of the J?
Well, so we leave up to you what version of Java you install.
I see. Okay,
Um, and lots of people just download the JDK and go with that, even though it's you know 4 or 5 times the size of what they need.
I see.
Um, the problem with us doing that is that if you're running an app that's using Java 2, then it's like, which modules do we strip out?
Right. Right.
Um, and if we had stripped out one of the modules that you need, then not good.
Yeah. Yeah.
So we stay out of the business of releasing JDKs. And so for people that want something smaller, um, JLink works pretty well.
Yeah. Well, that's fascinating, and I guess I just want to kind of close out here with a just one kind of like last question. Like what do you see yourself kind of doing? What's the next big thing that you want to sink your teeth into with this kind of technology? Maybe with green grass, or with something that lies beyond, or the fusion with generative AI. Any thoughts
Yeah,
there?
these days I'm back doing software developer tools,
Okay,
kind of high level stuff for um, people trying to build systems that are complicated. Um, the thing I'm working on kind of looks like some of the 4GL tools and the sort of wiring up boxes tools, but it's one where, you drag a temperature sensor onto the you drag a temperature sensor and say, okay, I want that temperature sensor to go into a chart, and it figures out all the software in between.
Oh, neat, neat.
Um, and the cloud layers, the time series database, um, it's a good chunk away from um, being a real thing, but um, I'm finding it pretty fascinating.
Yeah, yeah. And is that going to be something that's sort of accessible to sort of the world at large, or is it an internal tool, or
Um, who
who
knows?
knows? Okay, I won't ask further. Just for my
Well,
own.
no,
Oh,
I mean, you could ask. Um, I just have no answers.
I see. It just sounds something that I would love to use.
Yeah,
So
yeah. Um, but we'll see.
understood. Well, James, thank you so much for your time here today and talking about all these fascinating subjects. It was always fun being in the Java a toy show. I think it was referred to the keynote that I
Yeah.
used to do with you, where we had we brought some of the DARPA Grand Challenge vehicles that we were working on, and Link Bolt, Neil Young's car. That was a lot of fun.
Oh, yeah. I
Um,
mean, the toy show, um, as the sort of closing talk at JavaOne was, it was a lot of fun. I mean, the number of people that came in and just had built amazing things, and you were definitely a frequent flyer at the toy show. I mean, and like one of the ones that I loved that you haven't mentioned yet was you did that um, helicopter
oh yeah,
with the lidar map scanning,
yeah.
which these days is a pretty common thing. Back then, it was freaking wild.
It was a 6 foot. Yeah, it was actually a gas powered copter, 6 foot long. Had a lidar on it. They were using it for surveying, and we had it sort of fly over us when we were lying on stage. I remember that was a lot of fun.
Yeah, yeah. Except that the awful people who signed the insurance papers said, "Yeah, you can't actually turn the motor on."
I re-
So
I remember that. But do you remember when we brought in, it was, I guess it was one of Tommy Jr. We actually had it drive autonomously into the
yeah,
very slow at a slow speed into the Moscone Center area there, and there was like,
yeah,
I don't know, 20,000 people. It was pretty crowded.
yeah, yeah, yeah. And it had a kill switch.
It did. It did. It did. Oh
And,
yeah, and we had multiple sort of ways to shut it down, but it kind of crawled in. We actually just had it on idle, and so the car was moving just on idle speed, just kind of moving through at a very slow speed, and then we had it stop. So, but I don't know if they would do that today, but I guess it was okay. What was that in 2000? Maybe 7 or 8. I don't even remember. It was a while ago.
yeah, yeah. Well, I mean, some of the things that were done at Java One in retrospect were kind of stupid. Well, like the T-shirt cannon contests.
Oh yeah.
Um, there was one in particular where this guy, um, God, I can't remember his name, but he made this awesome, awesome T-shirt cannon. He could get like, if you tightly wrapped a T-shirt, it would go like half a
Oh
mile.
my gosh.
Um, and when the people whose job is looking after audience safety saw this thing, they kind of freaked,
Right.
uh, and they had him put on a governor, because this was like a compressed air gun, but the compressed air gun from
Right.
hell. Um, it had quite the compressor and quite the setup of air staging chambers. So they had him, ramp it down, and so then he got to do his shots, and then after he had sent t-shirts out over the audience, because he could get like the far back corner of the largest room at Moscone, with ease, right? And then he was done, the lights went down, and he decided to shoot one more t-shirt. So off went the restriction on pressure, and he just went, go for it. And he shot this t-shirt. I have no idea if it was an open air. I have no idea how far it would have gone, but it hit this concrete slab at the back of Moscone Center, bounced off, and a t-shirt is not exactly a bouncy thing,
Right.
But this bounced off, got into the audience, hit some guy on like the back of his neck, and he splayed forward.
Oh, no.
Took out a row or two of people in chairs and things. There was kind of a mess, and we were all going, "Oh God, please let this not end badly. This could turn into lawsuits."
Yeah.
And literally, the guy, scrapes himself up off the floor, grabs the t-shirt, and he yells, "I've got a t-shirt!"
Oh, that's classic.
That was like the end of the story. And so some of those stunts, they were fun.
Yeah. Well, that was always a fun show to do. And yeah, a lot of good memories from JavaOne. And I
Yeah,
guess they're doing it again this year. So
yeah,
to see
yeah,
what that's
well,
like.
yeah. Well, they'll, it's the kind of company that's more likely to be a little more sedate.
No t-shirt cannons, I presume.
At least not on the potentially lethal level.
Right. Well, James, thank you so much for taking the time. This has been it's great to catch up and a wonderful conversation as always.
Well, thanks for inviting me, and it's been fun talking.
Excellent. Well, thank you for everything you do. Thank you for inventing Java and giving all of us jobs.
Yeah, well, and thanks for having fun and letting the rest of us watch along.
It's
It's been pretty cool.
It's been a blast and we're still going. So, yeah, Java endures. Java endures.
Yep. Yep. Alrighty.
Thank you, James.
Thank you. Take care. Bye.
I hope you enjoyed the show Driven with me, Paul Perrone, your host. Don't forget to check us out at driven.show on the web and give us a thumbs up or subscribe here if you like the show. Thank you for listening in. See you soon.